This presentation will show many graphic scenes from the original video documentation taken immediately after the 1989 Loma Prieta earthquake in California. The program will focus on significant damage incurred at two Bay Area locations, the Cypress Freeway adjacent to Oakland and the San Francisco-Oakland Bay Bridge. Since that major disaster, California's Department of Transportation engineers have researched and devised new concepts to apply towards future seismic disturbances. They are currently being implemented as earthquake retrofitting on the state's bridge superstructures, footings, and columns. The genesis for the earthquake retrofitting program evolved from what was learned subsequent to the 1971 San Fernando earthquake in the Los Angeles area. Although most of this video will be narrated by Mr. Jim Roberts, Chief of Caltrans Division of Structures, some narration assistance will be provided by a fellow Caltrans employee. Mr. Roberts is a widely known, respected authority on the effects seismic forces generate on roadway structures. He is responsible for implementing and carrying out a $1 billion retrofit program on over 800 state bridges.
This picture shows the failed column joint. You can see the upper deck has collapsed onto the lower deck, and the reinforcing steel protruding from that column is number 18 bars, which peeled out like spaghetti, primarily because the confinement details that were provided by the code in the early 50s when this bridge was designed were typically number 4 or half-inch bars at 12-inch spacing. And they essentially were inadequate, as you can see, and the reinforcing steel pulled out. The joint just above the lower deck in the center of this picture failed, and the upper column collapsed and brought the upper deck down almost on top of the lower deck. This is a picture to give you a pretty good idea of the amount of movement that occurred at joints in the deck. A lot of damage to railings occurred because of the longitudinal movements. This again shows quite a bit of movement in most joints. This movement was restrained by the cable restraining systems that had been installed previous to the 1989 earthquake, subsequent to the 1971 San Fernando earthquake. So the movement in most cases was limited by the restraining systems, which performed adequately and essentially held the entire deck system on the upper level of Cypress together, so it came down in one piece.
This is the north end of the upper level on the Cypress Freeway. It collapsed and separated from the portion to the north. The northern portion, however, remained up in place. Readily seen are the girder stems in the top and bottom slabs. This entire section sheared off as a result of the earthquake. There were reports of wood inside the forms, evident near the top of this scene. The wood is the lost deck or stay-in-place forms. They support the upper deck, remain inside the box, and are typical for this type of bridge construction.
This indicates a small degree of movement of the structure against the surrounding soils, and it's pretty typical of the kind of evidence of earthquakes that's seen around structures on post-investigation. This is a section where the upper deck did not collapse completely down onto the lower deck. As a matter of fact, only one side collapsed here. So there's quite a bit of space left, and many hundreds of people were able to escape from this structure within hours after the earthquake. This is also a good example of how well these structures hold together during a seismic event when properly reinforced. This is a segment of the box that where the upper deck collapsed onto the lower deck, but the lower deck was able to hold. In fact, in 90% of this structure, which is 1.4 miles long, the lower deck stayed up in all but about 2 spans, and the upper deck collapsed on only the north half of this structure. This was not seen on the national news media, but the fact is that the southern half of this structure, while it was severely damaged, it did not collapse. You can see in the center of this picture the upper column where it has collapsed actually astride the lower portion of the bridge. You'll also notice that the cover concrete has been broken loose from the outside of the column reinforcing, and you can see the sparse confinement steel on this column, which again was standard detail of the time. You'll notice this is a segment where the upper deck collapsed down onto the lower deck. In most cases, the drop caps, which are lower than the bottom of the upper deck, landed on the railing, and so there was about a 4-foot gap between the lower deck and the bottom of the upper section even after the collapse. So there was space for people to get out and for rescue workers to get into the area.
Seen here is one of the few segments of the Cypress Freeway where the upper deck caused the lower deck to collapse. We're looking at the north end of the structure where it's separated from the approach ramps and where the double deck section separates and goes into a single level. For some reason, it's sheared off at this location. Just north of this break is a curve in the alignment, which probably provided enough stiffness that the straight section broke loose at this joint. This kind of collapse was typical.
Now this view shows a good example of the failure mode. Just above the small tree there at the top of the lower column was a lightly reinforced pedestal, which was much more lightly reinforced than the columns both above and below. And so that was essentially a fuse, to coin a phrase, and the structure broke at that point. And it broke simultaneously on both sides so that the deck dropped straight down and the columns straddled the deck, as you can see in this picture. This picture is in the vicinity of a railroad crossing underneath the structure, and there's approximately a 29-degree skew on these vents either side of the railroad siding, and all of the other vents are normal to centerline. We believe that just the added stiffness of having this vent on askew provided enough rigidity that the span did not collapse. The span is approximately 90 feet long, and on either side the upper deck structure broke loose from the span. You'll notice severe cracking in the joint area near the railing, the junction between the upper and lower columns. This is very typical of the kind of damage to these older non-ductile structures because of the lack of adequate confinement. Again, I must emphasize that this is the lack of confinement based on today's criteria. These structures were in fact designed for the criteria of the time. This is a view taken a day after the earthquake of the upper deck, and you'll notice that the deck is essentially intact because all of the hinge restrainer systems that had been installed in the 70s held the decks together at their joints, although the entire deck collapsed onto the lower roadway at this point.
This is a view near one approach abutment where the ramp comes from the ground level up onto the structure. Wherever the structure was connected to something that provided just a small amount of additional rigidity, it broke apart at that point. Not at a joint, but usually right in the middle of a span. These people are at the north end of the structure where the double deck separates to become a single level. This location is near the distribution structure between Interstate 80 and Interstates 580 and 880.
This is another view of that location where the upper deck broke loose, and you can see that the lower deck and upper deck are beginning to separate and go into a single level. So this is looking north at the north end of the structure. There were several fires, vehicle fires, on the lower deck, and the smoke in the background on the right side of this picture is some smoldering vehicle, the smoke coming from a smoldering vehicle. This is a segment where both spans collapsed onto the ground, and you can see the smoke in the background from the burning vehicle, which is on the lower level. This is a view of upper column segment that had completely broken loose from the cap and the upper deck, and the reinforcing steel at the right side of this column essentially peeled out of the cap, again because there was inadequate confinement. The major change in design since this earthquake involves about an 8 times increase in confinement steel to hold this concrete together and hold these joints together. This is an overall view of a section of the upper deck that had dropped onto the lower deck. You can see that the joint hinge restrainer cables have held the two segments together up on the left-hand side of this photo. Another view of a column that had slipped off its pedestal and straddled the deck. This view and several that follow here show the effects of soil liquefaction. Soil liquefaction was prevalent at the north end of this structure and on all the approaches to the San Francisco-Oakland Bay Bridge within a half mile of the north end of this Cypress viaduct. The material's been driven over and smoothed out by truck traffic by the time this photo was taken, but this picture here is a little more realistic of what soil liquefaction looks like immediately after an earthquake. There's small boils on the ground where the sand just bubbles up out of the lower layers. This picture is showing the false work that had to be installed to support the structure in order to facilitate rescue operations. This work began within hours after the earthquake on the night of October 17th, and we had to support the entire length of this structure. We were concerned that as the rescue workers cut holes in various members to extricate people, that there might be a failure, so we installed false work to support the entire structure. And these pictures are views of that false work. Within 4 hours of the earthquake, there were over 20 contractors mobilized and on site, erecting false work and providing security for the rescue workers. This picture is the West Grand Avenue overhead as we look east from the Bay Bridge Toll Plaza, and you can see the results of soil liquefaction and settlement in this area, which was considerable. The damage in this area was confined to approximately 4 bents. This is the most serious damage, and this was probably close to failure. It's the lower deck column joint, and there were 2 locations that exhibited this type of failure. These columns on the left-hand side are very long. They go to the ground. On the right-hand side, they're very stiff, and so the cracking occurred at joints. Now, this is a construction joint, but there's a lot of column damage here, and this is column shear in a short, stiff section of column. Very typical damage for this type of motion. And most of these structures were designed in the 60s prior to the advent of the current design code and design details, and they exhibited brittle fracture. But again, in a structure that's almost 2 miles long, the damage occurred in an area of about 600 feet, and it's over an old, deep creek bed that's been filled in over the years with non-engineered fill. So again, the damage here is very typical of damage that occurred throughout the region affected by the Loma Prieta earthquake. This is a typical roadway settlement at the wing walls of an approach to this viaduct. The soil underneath settles and the pavement drops. It's dropped about 3 inches in this location. This picture just shows some of the cracking along the shoulder of the roadway, again caused by soil settlement. This entire stretch of roadway near the toll plaza and easterly towards Emeryville is built on old deep bay mud, and that proved to be unstable in all the locations in the Bay Area and the Monterey area, Bay Area, where damage occurred. It was primarily where structures had been built over the deep, soft muds. This is just another example of the type of separation and cracking that occurs. These are fairly wide cracks caused primarily by soil settlement again.
We're now on the San Francisco-Oakland Bay Bridge and looking at the lower deck. A short distance away is the gap where a 50-foot upper deck span dropped into the lower deck. Really only the major damage to this bridge. We had some other locations that suffered minor damage. These problems were repaired by Caltrans maintenance crews.
Now this is the location of the upper deck failure. In the center of this picture you can see the bearing seat. One end of this girder span was fixed and the other end was on a sliding bearing to allow for movement as the trusses on either side of this tower bent flexed, and they also provided for thermal movement. During the earthquake, the easterly 300-foot truss moved 7.5 inches and came back 2 inches, so that there was a permanent displacement to the east of 5.5 inches. And when that occurred, this span dropped off its sliding bearing on the east end and fell onto the lower deck. When the girder spans in the upper deck fell onto the lower deck, it knocked the lower deck off of its bearings and dropped that deck onto the top of the 50 by 70 foot tower. This tower bent was put in the bridge, I'm sure, by the original designers in the early 1930s to provide for longitudinal forces. The forces that were used in the design were 7.5% G, and as we know today, we would design for at least 50% G at this location. Both spans in dropping wedged between the trusses on either side, so that the removal of these spans became a very complex operation. There was concern that we would cause other movements and failures, so the first step was to tie everything together with cables. The second step was to cut the deck in half because of its weight and the fact that it was wedged between the trusses. The floating barge crane that was brought out had a capacity of 250 ton, but that was not quite enough to lift the entire span, so it was cut in half. You can see some of the cables that have been installed by our maintenance crews primarily to hold these girders in place temporarily until the deck was replaced.
These are views looking west towards San Francisco at the dropped span. Yerba Buena Island and the Tower of the West base spans can be seen in the background. This picture is also at the 50-foot span failure location. The failure was caused by the shearing of 41-inch diameter anchor bolts in the bearings at each end of the truss, north and south end of the two trusses. The force to break the anchor bolts and overcome the friction resistance of members setting in place for 53 years was calculated to be over 2 million pounds. These pictures were taken during the removal operations.
This is the one vehicle that was crushed when the span collapsed, resulting in one fatality. Most of these photographs here are taken of retrofit contracts underway in the Los Angeles area, primarily because the structures in the Los Angeles area were more vulnerable than most in the San Francisco Bay Area, so the retrofit began down there. The technique is primarily to reinforce the footings and install steel jackets around these old non-ductile concrete columns. In this photograph, you can see the old footing, which is a darker concrete in the center, and the enlarged, reinforced footing. This is a view, again, of the workers working around the footing to add additional reinforcing and piling and increase its overturning capacity.
Typically, on these single-column retrofit projects, about 80% of the cost is below ground, and 20% of the cost is above ground. Even these architectural shapes have been retrofitted. The structural steel fabricators have done an excellent job in matching these shapes.
This is an auger that is drilling for the piling around the outside of the footing to increase capacity. Most of this work is more difficult than new construction because it has to be done underneath structures and it restricts the overhead clearance, so special equipment generally has to be designed to do this work. This retrofit work is being executed on approximately 800 bridges in this state, and by June of 1992 we had over 157 bridges completed and about 60 under construction, and all the designs for the remaining 500 or so are assigned to consultants or our own design staff. We have a legislative mandate to complete this retrofitting work by the end of 1993. This worker is using a rag tape to measure the depth of the hole. This is a cast and drilled hole piling. These orange marks on here are put on by the engineers to denote the location of additional reinforcing steel. Essentially, this old footing will be completely encased, top, bottom, and all four sides with a heavily reinforced shell. This view shows where the concrete's been broken back, and the reinforcing steel that extends out there will be lengthened by use of mechanical couplers, and then the new footing will be poured outside and over the top of this footing. One of the major cost items on this retrofit, as you can see from this picture, is traffic control. Quite often we have to take a lane and put up the barriers and so forth to keep traffic away from the excavations while we get this retrofit and strengthening completed. This is just a picture of some of the steel jacketing being installed. The advantage of this type of retrofitting technique is that it can be done with fairly light erection equipment. The steel jackets are typically half-inch thick plate and they're fabricated to the right shapes off-site so that the amount of construction work on the site is minimized. After they're installed, they're welded together and then pressure grouted to provide a tight fit. This following sequence of pictures just shows the plate. Now that's a half shell there that will fit around one half of the column, and it's an elliptical shape so that we maintain a tension membrane around the outside for a rectangular column. On square columns and round columns, of course, the steel jacket is a circular. That's just an erection dog there that's used to help hoist the steel jacket into place. And when the grouting is finished, these little pieces of metal are stripped off and ground flush. You can see in the center of this picture a pipe sticking out. That's the hole where the grout tubes will be connected, and the entire periphery between the concrete column and that steel jacket will be filled with grout.
This white material is styrofoam. It's placed between the steel jacket and the column in areas where we want to allow the column to move a little bit before it's restrained by the steel jacket. It's called a plastic hinge. It makes the column a little bit more flexible based on calculations for response. That particular detail is called a Type F detail.
In this case, the contractor is using his backhoe, which he also used to excavate around the footings for erecting the steel into place. This is probably not the smoothest operation we've ever seen in construction, but they got the job done, and this sequence shows them moving the shell into position and erecting it around the column. On the portions of the steel jacket that extend below the ground line, we use a mastic coating on the steel so that to try to prevent corrosion of the steel. And then above the ground it's painted a concrete color to try to match the existing bridge. The grout tube adapters are pretty visible in the center of this plate. Now this welder is attaching one of the erection dogs, as they're called. You'll notice that it's an angle with a hole in it. There's one on each side of the joint so they can put a bolt through and clamp the two plates together prior to welding. You can also see the backup plate, which is just on the operator's left hand there. That backup plate is in there so they can make a full penetration butt weld and then grind it flush and paint. On this column, on the right-hand side, you'll notice that the steel jacket is in place, and these workmen are placing the second half of the column retrofit jacket. All of the annular space that you see there in the center of this picture between the steel jacket and the concrete column is filled with grout. As you can see from this sequence of photos, the erection is complicated to a great extent because of the reduced overhead clearance, and so you have to be fairly innovative. And I think this crew graphically illustrates some innovative erection techniques. When the steel jacket is finally at its design location and the plates are pulled together at this joint, there's about a 1 to 2 inch gap left between the bottom of the steel jacket and the top of the footing, and that's so that when the column does flex and bend around in an earthquake, the steel jacket won't be damaged, and we want it to flex at the bottom and form a hinge. Now these workers are installing a bolt between the two erection dogs to pull the plate up tight. As soon as they close that gap, then the welding will proceed. Now you can see they have the two jackets pulled together. The backup plate is behind that dark band in the middle, and the joint's already prepared. It's been beveled so they'll come in with a welder and complete a full penetration but weld the entire length of the column and then take the erection dogs off. A good welder can weld about 8 feet an hour in this kind of an operation. He operates that platform himself as he moves down the column.
Cramped quarters here, but these workers are trimming the tops off of steel pipe piles. Afterwards, these pipes will be cleaned out and filled with concrete and reinforcing steel. This retrofit work, unlike new construction, is generally conducted in very cramped conditions. This traffic and other kinds of problems are typical of what the contractor often deals with. In the center of this visual, you can see the scaffolding that's been erected so the workers can get fiberglass jackets into place. The reason this is done with scaffolding is because this is a job in Griffith Park in the Los Angeles area. In this location, we're experimenting with fiberglass wrapping, which is about 3 to 4 feet wide. So the column is wrapped almost like an ace bandage. While the contractor has a machine that does the wrapping, scaffolding is needed to access the different locations. This fiberglass material has been tested, very similar to steel jackets, at the University of California at San Diego. Caltrans is experimenting with it on contracts to test its economic comparison with steel jackets.
The fiberglass on these columns is colored a gray in an attempt to match the concrete. This is an extreme close-up, but from a distance it's difficult to tell that these columns have been repaired. Now this photo is a view of a footing where the reinforcing steel is not being extended, but the shell around the footing has to be connected, and those holes are drilled so we can put reinforcing steel through there to provide shear transfer. This is a close-up. That concrete footing was originally poured against bare ground without forms, and so the surface looks a little rough, but it will be cleaned off before the new concrete is poured. Now this is a shear block that's just below ground on the side of an abutment. There's a huge piling below this block, and it's basically an external shear key to keep the structure from moving off its supports laterally. Longitudinally, it's tied inside with steel cables, but laterally these blocks have had to be placed here to provide shear enhancement. This is one of the fiberglass columns after it's been completed. As you can see from a distance, it looks good. When you get up a little closer, you see all of the imperfections. Now these are steel jackets on a architecturally shaped column up in Glendale at the State Route 134 and State Route 2 interchange, just west of Pasadena. These are stiffeners, and the only external bracing that has to be used on these columns where we have a flat surface. We don't want that to buckle during an earthquake. From a distance, driving by on the freeway, it's very difficult to see these brackets because most of the time they're in the shade. So to a motorist driving by this interchange, it would be very difficult to see any change after we've completed the work. This is a detail that's quite often used on steel girder bridges. These brackets are bolted to the girder and to the concrete wall here, primarily to restrain the girder from pulling off its support. You'll notice the slotted holes here in the connection between the girder and this bracket. So the girder can move a limited amount to provide for thermal expansion, but it will not pull off the support in an earthquake. This is a retrofit detail on an existing steel girder system. You can see the existing steel girder and its diagonal bracing in green, and the new angle, which is bolted to the abutment, has slotted holes in the attachment to the girder system. This is intended to keep the girder from slipping laterally or sideways off its supports, but it will allow longitudinal movement. This is a type of detail that will be used extensively around the state on steel girder bridges. This is an excellent view of a footing in the process of being reinforced and expanded. The white protrusions are the plastic sleeves through which the soil anchors will be dropped to provide additional overturning moment capacity for the footing. This view shows the additional shear connector stirrups that are bent like a paper clip there, which tie the new footing to the old footing. This is a close-up view of the sleeves through which the soil anchors will be placed after the concrete is poured.
You can see that, in this case, the footing is being reinforced on all four sides. Now, this worker is pouring grout into the holes to provide a bond between the new stirrups, or shear connectors, in the old footing that's been poured underneath.
As you can tell from this view, most of the work has to be done with heavy freeway traffic going right alongside the work areas. About a third of the cost of the retrofitting program really involves traffic control and traffic mitigation, so the work can be done without endangering the workmen and also without causing problems to traffic flow. This series of shots here, it pretty well shows the type of detail that's typical for single column supported bents, where there's really no redundancy in the system, and so we have to ensure against overturning during a seismic event, and we rely on the ductility of the column after it's retrofitted with a steel jacket to provide enough reserve energy and strength to survive through a major shake.
Earthquakes don't occur as frequently as hurricanes, tornadoes, or other types of natural disasters. But many countries, including our own, have been struck with seismic disturbances large enough and close enough to major population centers that significant devastation and losses have occurred. Earthquakes strike without warning, as was just seen in this program's Loma Prieta earthquake documentation. Records show that each earthquake leaves its own unique imprint of damage and tragedy. Perhaps this is nowhere more true than on California's bridges and structures. California was somewhat lucky in the damage sustained by the Loma Prieta event. When considering that there are 4,000 bridges in the 8 counties affected by the Loma Prieta disturbance and only 100 sustained damage, this region was indeed fortunate. 10 bridges were closed to traffic. 5 of those bridges remain closed today. Each earthquake provides engineers and scientists with some of the same lessons that have been pointed out by earthquakes in the past. Many of these historical lessons have and will continue to be applied toward goals of creating more earthquake-resistant structures. The intensive bridge retrofitting program in Los Angeles and subsequent California locations is a giant first step towards meeting these very important goals.